Yeah, looks good.
All right, perfect. All right, guys, I think we can start. So today, I hope you guys are excited. We're pretty much in our last week. And I know there's been a lot of questions. I'm hoping our professor and I can give you guys some light on that. But I think for today, we're going to just talk about just a few snippet of the problems that you guys have been working on. Mainly, if you guys have seen on Canvas, it says there's like part 1 and part 2. Probably the textbook problems. I'm going to talk about those, as well as like part 2, and I think one problem from part 1. But if there are other like problems that I'm not covering, just let us or the professor can probably answer those. But mainly, some of the problems I just picked out that like maybe good to talk about today are just like some of these, like the miss rate problem. I think this is like one of the first ones. And then this one is, I think, parity bits. I think this one is like the next problem after that, like 5.14. And there was also a problem about cost performance ratio and comparing those depending on like if you have like a 64-bit or 128. And then I think one of the good ones is like parity error, how you can correct that. If I'll give you guys some guidance, but not really give you like the full like exact answers for it. If there are like main questions for those, I know some of the solutions will lay it out correctly before the final. So I'm hoping that can answer some of those questions. And some of the other ones are replacement policy. And if you have like LRU, MRU, or a random one. And then I think I'll end it with this problem, the average memory access time. This was just one from part 1 that like we've been working on. So let's start with the miss rate. So for this, if you guys do have questions, let me know as I go to each problem. It may be better if you just ask as for each one. So for miss rate, this is kind of similar to homework 5, problem 5.8. So this is like the first one. And this problem just asks you like, what is a miss rate for this given like address stream? And it gives you like, this is the exact question, but to help you guys like what to look for, I kind of just kind of gave some guidance here. Some of the givens would be this video streaming workload access time. So it gives you that here. So this one would be 512 KIB. And then you also want to look for the sequence of address stream. So this is that right here. And then the difference between the address streams. So like if you have, for each one of these, I think it's like 1. And then you have this direct map cage size that's given to you. And then also the size of the cage line. So this is in bytes. So for us, it's 32. And then there's 2 problems on this. There's one that gives it to you in 32, and then the other one just kind of gives you more practice on how this changes depending on your cage block, or cage size. So those are the like 5 main things to look for. So in terms of like tips, what you would like, I would think what you would do in terms of a procedure is you would like find the block size first. So I just kind of provided here, kind of like an equation, maybe how you would, and you've seen this before, but for this one, how you do that is just you take this video streaming workload access time, and you just divide it by the cage size. And then the next thing would be finding the occurrence of the miss. So, or the miss, when does it occur? How I would do that is you take what you have, the given direct map cage size, and then what you just calculate, you just divide it by that. And then the difference between your sequence, your address streams. So when you do that, that gives you like how many times you're gonna have a miss. So the next step is kind of simple. You just take the the reciprocal of that, like 1 over that, and then this one, I mean, you give it in terms of a percentage. So just to note, I guess that this is just something. If there's some questions in there that you guys will explain, is like the miss rate is independent of the working set and the size of the cage, so it doesn't change. And there's also a question about prefetching. When you do the prefetching, you're going to see that it reduces the miss rate that you have. And I think for our particular problem, it's like nearly approaching 0. So yeah, for the miss rate, that's technically what you have to do. So you just get these 5 different variables, and then following this steps, you can get the miss rate very simply. So there's some variations of those, so I hope you guys get a grasp of that. But the next problem here is the parity bits. So this is similar to 5.14. I think this is like number 2. And then this is just asking you like the minimum number of parity bytes required to protect like maybe 64 or 128 bit. And it gives it to you, you have to do this for like 2 different types of codes, the SEC and DED. So these are just 2 different ways, but I'll explain, like there's a certain equation that you guys can probably refer to that can give you this answer. But before that, let's just look at like maybe some of the assumptions that that would be very helpful. But if you look at this problem, what I would say is you would just find like this P would be this is an equation in the book, but and then this P is your parity bits, and then if you're looking at for just to explain this equation first is so the number of bits that we can report an error is 2 to the P. And then the total number of bits here would be P plus 128. And then for DED, you just add 1 to it. There's 1 more bit to indicate that there's no error. So that's kind of like what this equation is showing. And then this is an equality. So like what I would do is find the P, that would be the minimum to satisfy this, and then that's how you would get the parity bits, the minimum number, because it's saying minimum number. So whatever the minimum here is what satisfies this. And then it's asking 2 things. So for the DED and then this SEC is you just add 1 more. So you add 1 more bit to what you get here. Or you can just solve this same thing. You just added just 1 here.
And there's a quickie shortcut you can do on that equation if you take log 2 of both sides.
Oh yeah.
The P, yeah. Now that saves you. It's a little bit quicker, but gets you the same place.
Yeah, that's really good. Yeah, instead of like doing the trial and error. Okay, and so that's really what it is. Just applying that equation. Like this is just me. In terms of tips, you would just apply that equation. Or try out different positive integers, or just the direct way of doing it for the smallest P. And for the SEC, same thing. So those are just 2 things. Just remember, like, what is it asking? Which equation do you apply? So those are like simple ones. And then now let's take a look at cost performance ratio. So this is also in 5.14. I think that's like part C or it's in the same group. But I just made this kind of general. This is not the exact problem. But what this is asking you is just compute like what is the ratio of like a code given A and a code given B. So that could be like 64-bit or 128 or any number. But just to give you like maybe some of the assumptions I would make for this to help out is, so like the cost that it's shown here is just mapping it with the number of parity bits. So that's what it is. The cost is like the relative number of parity bits. And then the performance is the number of error, or like the error number that you have, which I'll explain in a bit. But for example, let's take a look at this one. So like you have a 64-bit, and that's your like code A. So how long is this parity bit? It's 8-bit long. And then, so that would be your cost. And then for 128 is 9. So knowing those, that's what you have for your cost, because there's just two variables there, the cost and then the performance. And now looking at like the performance. So like looking at like the maximum error pattern, from that, you just count the number of ones, and then the number of ones is what determines like the error number. If you have 1 0 1 0 1 0 1 0, that's like 4, and then so you just count the number of ones, and then that's for this question, it's like asking you like find the cost performance ratio for each one of these, and then find the ratio of that. So what you would do is like you just take the number of parity bits, divide that by the number of error, or cost divided by performance. And then the ratio that would just be for this program, what you find, and then over this program. And then you're gonna see that after you find this, you might see like the 64-bit. You're gonna compare this. Might have like a higher ratio over the 128. So that kind of leads me to the tips here. So first of all, you're given code A, and this is just like showing it directly what I would do. So for this, you count the number of parity bits, divide it by number of error, and the same with B. And then you're gonna see like for cost performance ratio, it's asking you which performance is better, or which code is better. I think from what I got is whichever code has a higher value. Typically, this is the better code, like in terms of this ratio. So which one has a higher value? So that would be like the better code. So that's a question that you might come across. So for cost performance, it's just applying like what is the cost and then what is the performance, and then like just remember like how to get them. Like the cost is very simple, and then for the error pattern, you just count the number of ones, and then you just compare those. And this leads me to the parity error. So this is also in 5.14, and in part 2, problem 2. So for this, so for one of those codes, SEC or DD, you're given like a word and then a parity bits, and then also a hexadecimal value, which you guys have to expand into like data and position. So and then from the parity value, you're gonna see if you have an error, and if you do, then you have to correct that. So some assumptions I would probably make for these problems is that the parity bits are used. The SEC could consider a single error pattern, but then the parity bits are used for error checking. So I'll show that in a bit. So the binary value, like you're gonna convert the hexadecimal value. It can be you can represent this as like you can break it down to like a parity and data values, and then how you find the error would be if there are even number of ones from the data, and when you check and then how you correct that is shown here. I'll tell you guys. So once you see that there's like a parity error, then you just invert that data. So like if you have like a 0 for that, then you make it into a 1, and if you have a 1, you make it to a 0. So like the other tips here is like the first thing you would do is like for the bit data pattern, kind of like if you have the parity and then its position. So try to like create a table for those. And then this hexadecimal value here, you would want to expand it into its binary equivalent. And then you use that as your data value. And then you enumerate the position, like the number of digits you have there would be its position. And for each one of those, what you would do is you check the position with its data. So like that's how you know, like for each like parity value, you would check if you have an odd number of ones for the data value, or like an even number of ones. And I think from what I got is if you have an even number of ones, there's no parity error. And if you have an odd number of ones, there is. So you're gonna compare that for this problem. Like there's like 4 different like parity values, and then you're gonna see which one has an error. So just remember the even number of ones after you count that data value, and that's when you expand the hexadecimal value. You're gonna find the even number of ones for each parity. And then how you correct it, because I think this is asking, you correct this error. You would correct this error by just like you go to the parity value. Like for example, if it's like 6 or 8, then at the data value there is like 0, then you just change it to a 1. And then if it's like a 1, you change it to a 0. So that's how you correct that. So that it's not like.
Yeah, Paul, let me just jump in real quick. There's a time saver for doing this. Do it graphically. Use that table that shows bit positions, parities, the one that I stole from Wikipedia and pasted into the lectures. Have that ready to go. It's got to be a huge time saver when you figure these out.
Yeah. Yeah, if you graphically do this, it's really like, as I said, like you have the position and then the data and then PD values, and then like once you know what position, and then just change the data value. So yeah, those are the steps. I mean the steps are if you create that table, like the pictorial will really help out in pointing out which one you're gonna change. So that will be very helpful. And then for this next one, replacement policy. I think this is problem 5.2. For this, I'm just gonna give you some tips. I'm not gonna like show you guys like how you would solve it, but for replacement policy, so for each like address sequence, you would just have to update the cage and assess whether it's a hit or miss. So again, like you would have to create a table on this one, and then update the cage if you need to. If when you get a miss, you would update the cage, and then when you get a hit, you don't have to. So it just transfers over, and it's difficult to. There's a few conceptual questions in here. And just to talk about those, when you're replacing a cage and trying to optimize that for all address, it's sometimes challenging because it requires feature knowledge, maybe the reference string. So that's just a tip if you guys are struggling with those. And there's also one question. It was tough to find this one, but when you're making a decision about your memory reference, how it affects your miss rate is it would bring down the miss rate. Like it's going to reduce it. So it's equivalent optimal like algorithm. And then so those are just some things for the replacement policy. I would just like look at create a table again and then update each one of these. And for part 1, there was a problem here. I think in problem 2. There's like average memory access time. It doesn't give you an equation. I know for a part 3, it gives it to you, and then you just have to find what those are. But for this one, you would just have to apply like this. I just gave this to help out. Is you find this T average by it gives you like a percentage hit rate, and then you just times that by the time of the memory plus the TLB, and then you add that to 1 minus the hit rate that you are given, and then you just add these values. So I'm hoping that this can this equation will give you like the right answer, but there's a few things there to just you guys can just add to this. So and then there's other questions about the, let me see, I can show you guys this. The disk access time, and it does give you that equation, the T data equals T seek plus T rotation plus T transfer. So for those, T seek is already given to you, and I think this is like part 1 of problem 3. Just apply that equation, and you should be able, like with the given values, and you should be able to get T data. And I think that's what I have for today.
Okay, so if anybody else would like to go through